moving to our third session, I would like to invite Dr. Mohammed Mohsin, session chair. Dr. Mohammed Mohsin, kindly chair this session. Over to you, sir.
Okay, thank you, Mr. Danish. Now, I welcome all the participants to this session. This is the last session of today's, and this session, in the topic of this session is data science in reliability analysis of safety critical software systems. Dr. Lalit Kumar Singh will deliver this lecture. Dr. Lalit Kumar Singh received his PhD degree from IIT BHU. He has been working as scientist in NPCIL, Nuclear Power Corporation of India Limited, BARC, Department of Atomic Energy, Government of India, for the last 20 years. He has distinction of working on pressurized heavy water reactors and light water reactors. He has an illustrious career and successfully completed several critical challenging jobs. His assignments included design, development, testing, related research, and site validation of the safety critical computer-based systems of Indian nuclear power plants. He has published several research papers in reputed journals like IEEE Transactions, IEEE Computer, ACM, that is Association for Computing Machinery, etc. He has been invited for chief guest keynote speeches, session chair, and talks in many international conferences, short-term courses, workshop, and faculty development programs from many IITs, NITs, and other institutions of national importance. He is recipient of many awards like Publication Award, Group Achievement Award, etc. He is reviewer of several SCI Index journals, life member of Indian Nuclear Society, founder member and industrial coordinator of the proposed Center of Dependability at IIT BHU. He is in the panel of Faculty Assessment Committee of the Department of Computer Science and Engineering IIT Roorkee. He is a member of editorial boards of many reputed journals and guest lead editor of many special issues. He is supervising many PhD students of different IITs, NITs, and is also PhD thesis examiner of IITs, NITs, and other reputed institutes. He is an expert member of Industrial Policy Formation of IIT Roper, Board of Studies of many autonomous institutes, and member of the advisory board of many institutes and universities. He is a reviewer and project collaborator of research proposals of Board of Research in Nuclear Sciences. He is also the faculty of Nuclear Training Center, Department of Atomic Energy, Government of India. He is interfacing with other countries like Russia, USA, France, etc. for importing nuclear reactors that are based on new technologies. His research interests are in the area of reliability, safety, and security of safety critical computers based systems. Now, I welcome you, sir, and I would like that you should start your expert lecture on your topic. And I also hope that the participant will be benefited with your lecture. Thank you so much for giving your precious time to us. Please start your lecture.
Thank you, Dr. Mohammed Mohsin, for the introduction, and I would also like to thank all the organizing committee members who has provided me this opportunity to share some of the experience to all the participants. So I think I have not been given the permission to share my slides, so I'll be requesting you to please permit me to share so that I can share my slides.
Okay, Dr. Danish, please do the needful.
Yeah, thank you. I have got. So I hope the slides are visible. So I'll be talking on data science in reliability analysis of safety critical software systems. So to start with, let me first make you understand about the topic, what actually this topic means. And then I will draw the motivation after explaining the essentiality of this topic. So to start with, the safety critical systems are those systems, the failure of which can lead to the catastrophic disasters, or even it can lead to the loss of human life. And hence, such systems do have very high dependability requirements, and that include reliability, safety, performability, and these are the dependability attributes. And there are the wide range of applications where we use the safety critical systems, for example, aerospace, military domain, defense, automobiles, medical domain, nuclear domain, space. And most of these systems are software systems or are being controlled by the software. And and hence such systems do have the very high reliability. If you talk about the reliability, it can be defined as probability of the system, probability of the failure-free system up to a given period of time under certain environmental conditions. So this definition is very important. When I say it is a probability of a failure-free operation of a system, it means its value range from 0 to 1 if I talk with respect to the quantification of the reliability, because it is a probability, and so its value will be from 0 to 1, and 0 means least reliable and 1 means highest reliable. And probability of failure-free operation means success operation of the system. Then in the definition, I said up to given period of time. It means when I talk about the reliability of any particular system, I'll also have to tell up to what period of time I'm talking about, because nothing can be reliable for infinite period of time. Even if you recall your old days, you would be thinking that time like, okay, these are my best friends and they are going to be forever. But as and when you started growing up, your dynamic scenarios keeps on changing, your interest keeps on changing, and it may be like, new friends started replacing our old friends. So what I mean to emphasize that if you talk about the reliability, you'll have to also talk about the target time, or up to what period of time you're talking about. Then I said under stated environmental conditions. So reliability depends on the environmental conditions or the operating conditions. And to realize this fact, for example, suppose you purchase a refrigerator and you go, the vendor gives you a warranty period of 1 year. And suppose you bring back that refrigerator from your in your home and you throw it from 14-story building, then it will collapse. And then if you will go back to the vendor to ask for its replacement, what he will say, look, you have not operated this product under the stated environmental conditions, and hence this warranty period has been voided. So I want to draw the 2 points over here, that reliability is a function of time. So up to what period of time we are talking about, it is very important, and it depends on the environmental conditions. And definitely reliability is, if I want to measure the reliability, basically I'll have to deal with the data, with the system data, success data, failure data, malfunction data, and hence the data science plays an important role in performing the reliability analysis. So to start with, let me go through today's outline. So introduction to reliability and background, I have already given the enough introduction, but it's definitely, we will see the mathematical representation of the reliability. And then I will be introducing FactoryNet, which is a mathematical and graphical tool, and which is basically used to model the stochastic processes. So if you want to categorize the processes, it can be done into 2 parts. One is the deterministic processes and second one is the stochastic processes. And deterministic processes are those processes, the outcome of which can be 100% guaranteed. For example, suppose I do have a pen in my hand, and if I drop a pen, I can 100% guarantee it is going to fall down on the earth because of the gravitational force that is active. So I mean to say, like, I can 100% guarantee about the outcome of that process, and hence it is deterministic in nature. While the stochastic processes are those processes whose outcome are not 100% guaranteed in spite of rigorous planning or systematic planning. For example, suppose I need to attend a meeting in Hyderabad at 4 p.m. and I'm located in Mumbai. And considering all the local traffic delays and flight delays and local traffic delay at Hyderabad, suppose I start here at 11 a.m. But then also I may miss my target, and the reasons could be manifold. The reason could be, for example, if I'm going to the airport from the normal route, and after going through almost 10 to 15 kilometers, I came to know like some road construction is going on, and I have to deviate my path, which is much longer than the normal route. So it could cause the excessive time delay, which I might have not postulated while my planning phase. The other reason could be there could be flight cancellation or excessive flight delay because of some technical or administrative reasons. So I mean, there is some randomness in the system, and randomness means the thing which is not known in advance to us. So we say it is a random in nature because the things are unknown to us. So I'll be introducing the Petri nets, which are able to model the stochastic behavior of the system. So I'll be introducing the basic building blocks and the modeling construct and the working mechanism of the Petri nets. Then I will touch upon the properties and analysis technique, and then I will be introducing the reliability prediction framework, in which I'll be emphasizing the various phases that are required to be carried out for quantification of the reliability of the particular system. And in each phase, what all the activities that needs to be executed, I will also touch upon. And here we will see like where the MATLAB and all those will be used for the data analysis, and then I can conclude my session. So let us go through the mathematical definition of the reliability. So suppose let X be the random variable that represents the time to failure of a component. I mean, because the system comprises a lot of components. So X is a random variable which is representing the time required to fail a component. So if my target time is T, then the reliability of the component at time T will be given by Rxt. As I said, the reliability is a function of time, will be equal to probability that the value of this random variable must be greater than T. Because if this will be less than greater than T, it means it is failing before the target time. So it will not be reliable. So for the condition for my component reliability is that failure time must be greater than the target time. Means it should fail after the target time gets completed. So from the total probability law, it can be equated to 1 minus probability that X is less than or equal to T. And what this X is less than or equal to T means, it is the probability that your system has failed before the target time. So it is the failure probability. So it can be written as 1 minus failure probability, which is also a function of time, and notation is Fxt. And this failure probability I can write down as unreliability also. So the reliability is equal to 1 minus unreliability. Now let us look at some of the traditional methods for the quantification of the reliability before going to the Patrinet modeling technique. So one of the prominent model is the reliability block diagram. And it is a series and parallel reliability block diagram that represents the logical structure of the system with regard to how the reliability of its component affects the system reliability. So for example, if I do have a laptop as a system, so there could be the various components that includes electronic components or mechanical components. For example, your ICs, different ICs, capacitors, transistors, your keys, push keys, mouse, push buttons, screen, and these are the different components and which are arranged in series or parallel logic. And if the components are arranged in series and having the reliabilities and having some reliabilities, then I can compute the total system's reliability by multiplying those components' reliability. So for example, I do have a system and having only two components, C1 and C2, which are arranged in series and having the reliability R1 and R2, then the system reliability will be R1 into R2. And if those components are arranged in parallel, then the system reliability is equal to 1 upon R is equal to 1 upon R1 plus 1 upon R2. Then the reliability graph, which is also a prominent model, and it consists of a set of nodes and edges where nodes represent the link between two components and R represents the components in the system. So if you look in this figure, the left figure is the reliability graph where nodes which are A, B, C, D, these are the component connectors, and the V and the arcs like V1, V2, V3, V4, and V5. These are the component itself, and hence it can be transformed into the reliability block diagram, which is shown in the right side. So you can see like all the vertices are replaced by the connectors and all the V's are replaced by the component itself. And it is a reliability block diagram. And you can see these are the 5 components where the component 1 and 4 are arranged in series, 2 and 5 are arranged in series, and then these 3 segments are arranged in parallel. So you can use the series and parallel reliability formula to compute the overall system reliability. Now the next one of the very prominent model is known as Faultry, which represent all the sequences of individual component failures that can cause the system to stop functioning in a tree-like structure. For example, suppose if I say the failure observation is human is not able to see, then I'll have to deduce the reason, and the reason could be his left eye is not working and right eye is not working. So I will have to put AND gate because there will be the AND logic. And suppose the probability of the failure that left eye is not working is P1 and the right eye is not working is P2 respectively, then the probability of the failure of the human that it is not able to see, it will be equal to P1 into P2. So if the events are arranged in the AND logic, you have to multiply the basic failure probabilities. And if they are arranged in OR logic, you have to sum the basic probabilities. And because the top event will give you the failure probability, so you have to subtract it by 1 to compute the reliability. Now, the models that we have looked so far, these can be solved using the FAST algorithm, but it assumes the stochastic independence between the system components. Means if suppose one system contains 3 components, I will have to assume like these components can fail itself independently, and one component cannot fail because of other component. But in real scenario, this is not applicable at all, and hence the assumption that the failure or the repair of the component is not affected by other components is not practical. And if you will model such kind of component dependencies, you have to use the powerful model. So if you want to model more complicated interactions between the components, there are the models like Markov chains or Faultry nets. These have the potential to model such dependencies. So if you look into the Markov model, the concept was introduced by Andrew Markov, who was a Russian mathematician in 1940s. And he said, like every system can be composed of various states, and it can be broadly categorized into the behavioral states and failure states. And behavioral states are normal states. For example, if human is a system, the behavioral states could be running, eating, moving, talking, walking, sleeping, and the failure state could be meeting an accident. So if and definitely from one state, I can transit to another state. For example, if I'm eating, I can transit to take rest. From taking rest, I can transit to move. And if I'm able to somehow find out the probabilities of a probability of my system being in all the states, then I can compute the reliability by summing up the probabilities that a system in all the behavioral states. And I can find out the failure probability by summing up the probability that my system is all the failed states. So, and from that also I can compute the reliability by subtracting by 1. So Markov models are the most powerful tools for the reliability or the safety analysis because they provide the modeling capability of all sort of dependencies. And if you look into the basic construct, it contains a set of states and the transition probabilities among those states. So before going to the framework, I will introduce to some of the mathematical concepts that we will be using in our framework. So suppose there are the 2 states, I and J, in a Markov chain, and let Qij is the transition rate from state I to state J. Transition rate means number of transitions per unit time. Then we can define the transition rate from state I to self state by equating and summing that will be equal to minus sum of all the transition rate from that state to rest of the states. And this is what this formula is. And then we can define a term known as the transition matrix or the transition rate matrix, in which I'll have to define the matrix where the rows and columns would be there. And on the row side, you can write down all the states of that system. In the column side also, you can write all the states. And then you can fill in this metric element by the transition rate from one state to rest of the states. And that will give you the transition rate matrix. and we can term it as generator or transition matrix as well. Now coming to the Petri nets, as I said, it is a very good graphical and mathematical tool. And why graphical tool? Because I can model the system behavior. I can model the system behavior graphically, and all the stakeholders may involve and to see like what is the system specification. And why it is a mathematical tool? Because I can embed the mathematical knowledge into the tool, and I can solve various equations, state equations, to know more and more insights about the system. So specifically here, we will see how we can solve the reliability of the system. So before that, if you look into the history of Petri nets, as I said, the concept was introduced by C.A. Petri, who was a PhD student or the research scholar, German research scholar. And he introduced this concept to model the stochastic behavior of the system. And after going through the thesis, the people were taking interest to explore whether this modeling construct can be used to model the concurrent systems or the parallel systems. And with this objective, MIT USA conducted a conference on concurrent systems and parallel computation in 1970s. And the conclusions were very fruitful. And they were like very keen to explore or to strengthen the modeling power to solve more and more industrial problems or challenging problems, real life problems. And with this objective, again, they decided to meet after 5 years. So in 1975, MIT USA again conducted a conference on Petri nets and related methods. And after that, it started gaining popularity in the industries, and looking at the industrial demand, a course on general net theory of processes and systems was started in Germany in 1979. And the people from different domain, like medical domain or aerospace domain, they were also started taking interest whether this Petri net will be able to model their particular specification, their particular systems, specialized systems. And with this objective in 1980, the first European workshop on applications and theory of Petri nets was conducted in France. And after that, the researchers came out with the different flavors of the Petri nets. For example, if you want to know the performance of the system, definitely the timing plays a very important role if you are working on the real-time system. So a Petri net where we can embed the timing information are known as a timed Petri net. And the first international workshop on time Petri net was conducted in Italy in 1985. And there are a lot of other flavors of the Petri net which keeps on coming up. So this is not an exhaustive list, but it just mentions or gives a motivation starting from the origination of the concept of Petri nets to the various milestones that the Petri net have achieved and how it became so popular. And if you look into the applications, definitely the variety of applications can be modeled. So now coming to the Petri net modeling construct. So suppose to start with, I want to model a very small chemical reaction, which you might have all studied during our 10th or 9th class. That is 2H2 plus O2 that gives 2 molecules of water. So before going to the modeling of this equation, first I will, the model of this equation is this figure. This is a Petri net figure, but before going to the modeling and the working mechanism of the Petri net, I would be liking to introduce the basic building blocks of this Petri net. So if you are able to see, there are the three big circles, and these big circles are known as places. So there are the three places, and I'm representing one place. I'm using one place to represent hydrogen, one to represent oxygen, and one to represent water. The next building block is the rectangular bar. If you are able to see, there is one rectangular bar which is known as a transition, and the places can be connected with the transitions with the help of a directed arc. And so there are the three directed arc in this figure. If you are able to see, which is one is connecting hydrogen place to transition T, one is connecting oxygen place to transition T, and one is transition T to water place. And every transition has a weight on it. I will tell you the significance of this weight, but right now I'm focusing only on the basic building blocks. So if you see, the weight of the arc which is connecting hydrogen place and transition T is 2. The weight of the arc which is connecting oxygen place and transition T is 1. I have not mentioned any weight. So if I don't mention any weight, by default, the weight is treated as 1. Or explicitly, if you want, you can mention a numeric 1 over here. And the weight of the arc which is connecting the transition T and water is 2. And now one more basic building block. If you are able to see the embedded circles, solid circles inside the places, and these circles, for example, the hydrogen place contains 2 circles, and these circles are known as tokens. And here I am representing the token to represent the atoms, because hydrogen contains 2 atoms and oxygen also contains 2 atoms. So I'm representing it by these 2 tokens. And now one interesting fact is this distribution of the tokens among the places in a Petri-net figure represent the state of the system. So if you look, the state of this system is 220, because hydrogen contains 2 tokens, oxygen contains 2 tokens, and water contains 0 token. And this state is representing the left side of this equation, that is this chemical reaction, that is 2H2 plus O2. And now I have to change the state. It means I need to convert it into the water. So as I said, the state changes can only be, the state is represented by the distribution of the tokens. So if there is a change in the state, the distribution of the tokens will have to change. But there is a rule how the distribution of the token can be changed. So the rule says that at least one transition in the Petri-net figure must be in enabled condition. And because this Petri-net figure contains only one transition, and so this transition must be in enabled condition. But what is the enabling criteria of the transition? The enabling criteria of the transition is that all the input places must contain sufficient number of tokens. I repeat, because that is important. The enabling criteria of the transition is that all the input places must contain sufficient number of tokens. But who will decide the sufficiency criteria of the tokens? So if you look with respect to this transition, the hydrogen place and oxygen place are the input places, and the water is the output place. So the sufficiency of the tokens will be totally decided by the weight of the respective arc, where the significance of the weight of the arc comes in. So if you look in this figure, the weight of the arc connecting hydrogen place and the transition T is 2. and hence hydrogen place must contain at least 2 number of tokens. Similarly, the weight of the arc connecting oxygen place and transition T is 1. So the oxygen place must contain at least 1 number of tokens. And hence this eligibility criteria fulfills over here. So the token distribution can change by movement of the tokens from the input places to the output places. But how many tokens will be moved out and how will be deposited from the input and output places respectively, that also will be governed by the weight of the respective arcs. So if you look here, because the weight of the arc connecting hydrogen place and transition T is 2. So after firing of the transition T, because T is enabling, so T is in enabled condition, so it will fire. And after firing, the 2 tokens will be moved out from the hydrogen place. Sorry, not oxygen, hydrogen place. And because the weight of the arc connecting oxygen place and transition T is 1, so 1 token will be moved out from the oxygen place. So in total, the 3 tokens will be moved out from all the input places if I sum up. But how much will be deposited in the output place, that will be also governed by the weight of the output arc, which is 2. So the only 2 places will be deposited in the, only 2 tokens will be deposited in the water place. So one interesting fact I want to bring here, there is no law of conservation of tokens, because you can see, although the 3 tokens has been moved out from all the input places if you sum up, but only 2 tokens are deposited in the output place. And now the state will be like this. So 2 tokens has been moved out from the hydrogen and 1 token has been moved out from oxygen and 2 has been deposited in the water place. So this is now the right side of this equation, and you can see now the token distribution is 0, 1, 2. So this is the state. And now again you can check whether your transition is in enabled state. So now it is not enabled state because hydrogen place does not contain the sufficient number of tokens, and it should contain 2 tokens. Although the oxygen place contains, but there should be AND logic, not OR logic. So one interesting fact I want to emphasize that it also helps in identification the number of possible states in the system throughout its operational time. And here I want to introduce a term known as a reachability graph. As I said, it is a graph, so it contains nodes, and nodes are nothing but it's a state. So it is the distribution of these tokens. And one state can transit to another state by firing of the transition. So R represents the firing of a particular transition. And I want to introduce a Markov property mathematically. So a very interesting Markov property says like the next state of the system will always depend on the current state of the system and not on the previous state of the system. So how mathematically we can represent it? Suppose there is a sequence of random variable x1, x2, x3, and so on. Then with the Markov property, that probability that my system is in n+1 state is equal to x will be depending on only the probability that my system was in nth state and not on the previous states. And so I can write it down this equation. And this is the Markov chain representation. It is just a random example just to show, just to represent how I can represent the Markov chain, which is containing the 2 states S1 and S2, and S1 can transit to S2 and vice versa. And this is a random slide just to show how we can draw the reachability graph. So if you look into this M1, which is a state, and state is represented by the distribution of the token. So suppose there is a PetriNet figure which contains the 7 places having the distribution token distribution 1 0 0 1 0 1 0. And this state we can term as marking also. So this is suppose M1, and after firing of transition T1, suppose the token distribution has changed like this, which is represented by M2, and so on. And this is a reachability graph, which can be equivalently converted into the Markov chain. So all these M's are nothing but are the states. And in the Markov chain, I represent the states by the circle. So all these are these 1, 2, 3, 4, and all the arcs are representing basically the transition rates from one state to another state. Now let me introduce the reliability prediction framework, and which contains the 3 phases. One is the creation of the PetriNet model of the system. The second is the converting that PetriNet model into the Markov chain. And the third one is reliability computation. So first two phases we have already seen, but definitely we will take a real case study in which I will again emphasizing on these 2 phases. And the third phase also I will be demonstrating how we can use the mathematical knowledge for computing the reliability of that particular system. And before that, before going to the case study, I would like to introduce some of the mathematical concepts which are very important. So let pi IT be the probability that a component is in state I at time t. And as I said, the state could be the failure states or behavioral states. So there could be M failure states from F1 to Fm, and there could be N behavioral states from P1 to Pn. Now, as t goes to infinity, which is a time basically, all these probabilities converge to the stationary distribution. This is a very important concept, and I want to introduce with the help of an example. What does it mean basically? If your system is complex, it will take more time to settle down or to reach or to stabilize for stability. For example, if I do have a glass and I fill it with water, and if I put it on a table, you will see like initially the water will be zigzagging in the glass, and then after some period of time, it will settle down. But if you try to replace this glass with a huge container, probably at the size of your room, and then you fill it with water and you put it down somewhere, you will find that a huge amount of time will be required in this case to settle down the water as compared to the glass. And hence, when your system is more complex, it takes much time to reach to the stationary distribution. So theoretically, I have assumed that if t tends to infinity, all the probabilities will converge to the stationary distribution, irrespective of the complexity of that particular system, and which can be computed by the 2 equations. The first equation is very simple. It only says like the probability that a system is in all the states. If you sum up those probability, that will be always is equal to 1. So it is from the total probability law. And the second equation is I would like to explain the second equation with the help of the same example where I have taken the huge container filling with water. And suppose at the initial time t is equal to 0, the state of the water is S0. And the S0 after, where the water is very zigzagging, and after suppose some period of time, for example, delta t, it is propagating towards a more settling process. And probably after delta t, it reaches state S2, S1. So S1 will be depending on the S0 into the transition probability from S0 to S1. And further from S1, after delta t time, suppose it is propagating towards more settling process and it reaches to S2 state, then again S2 will be depending on S1 into the transition probability from S1 to S2. And suppose at nth state, that is Sn state, my water is completely settled down. So definitely what will be the n plus 1 state? It will be the same as Sn because it has already been settled down. But the equation remains same. What was the equation? That Sn plus 1 is equal to Sn into the transition probability from Sn to Sn plus 1. And this is what the second equation is. That is, the final state is equal to just previous state, which will be same in the case of stationary distribution. And you have to multiply by the transition probability matrix because you are considering more than one state, and hence you have to multiply by the matrix. And you can solve these equations using MATLAB. Okay. And so now let us try to take a case study in which I'll be demonstrating how we can apply this prediction framework on the case study. And you can solve it in the MATLAB also. And so suppose there is a system containing only two processing nodes. One is the embedded unit, which is acquiring the data from the field sensors, which contains some temperature, pressure, or something like. And it, after processing the data, the raw data, it is transferring that data to the display unit. And so let me try to compute, because this is a very important system. It may be a real-time system and a life-critical system. So the communication plays a very important role, because if wrong data gets transferred from the embedded unit to the display unit, a wrong action can be taken up, which can lead to severe consequences. And hence I am interested to quantify the reliability of the communication module. And the communication module is very simple. The way for example, if I want to talk to my friend, I lift my phone, I dial the number, and after it starts ringing up, and after he picks up, I say hello. And then I wait for the acknowledgement. Suppose if I don't get the acknowledgement after a certain period of time, I will again say hello. And again, I will wait for the acknowledgement. And I will repeat it till I don't get the acknowledgement. But after a couple of tries, if I don't get the acknowledgement, I will assume that there is a loss of connection, and I will cut the call and I can retry again. And the same communication module is basically the protocol has been applied in this case also. So when the embedded unit sends a new packet, the value of the variable, I have kept one variable. You can simulate all these in the MATLAB programming. The value of the count, you have to set it 1. And the embedded unit, then it has to wait for the acknowledgement for time t1 after sending the packet. And if embedded unit receives the acknowledgement before time T1 packet send, that before T1, then the packet send will be successful, and I'm keeping one variable known as semaphore variable, which is changed to its complement. And if count is less than n and the acknowledgement is not being received, then the embedded unit transmits the packet and set count is equal to count plus 1, because it has to keep the record how many times I have sent the packet. For example, how many times I have sent hello, because after a couple of trial, if I don't get the acknowledgement, I will cut the call and I will retry. So the similar philosophy over here. So if the count is less than n, then only it will keep on incrementing the count. Otherwise, the embedded unit will terminate the send process unsuccessfully, where the semaphore variable will not be changed. And if the T1 time elapsed after the last data sent, I will destroy this semaphore variable. And now this is the protocol that we have seen, and I have to model it with the help of the Faultry. And this is the Faultry model. So let me explain this Faultry model. So one interesting point here, you can see like all the weight of all the transitions, or weight of all the arcs, sorry, not transitions, all the arcs are 1. So, and now coming to, there is a place PSRDY0, which represent that embedded unit is ready to send the packet with some semaphore variable setting to 0. So if there is a token in this place, it means embedded unit is ready to send the packet. Now one more place I have taken, in which at the initial time I have put the token, which is TDSR, and it represents that the embedded unit gets request from display unit to send the data. And then if both the condition will be applicable or hold, then the embedded unit will send the packet with sequence number 0, which is represented by this transition TS0. And here we have to set the value of the count K is equal to 1 by firing this transition, because it will keep a record how many trials we have done it. Then PSW0 place, it represents that after sending, this embedded unit is waiting for the acknowledgement for that particular sequence number only. So every packet has been stamped with the sequence number, so that I can have a trace whichever has been reached there and what packets are lost, so that I can send the packet, those lost packets with the sequence number. So sequence number helps in identification of success and loss of the packets. And when the token will come in PSW0, it will represent that embedded unit now is waiting for the acknowledgement with the sequence number 0. And but if there will be the timeout, which can be represented by the transition TSW0, and it represents that embedded unit detects the timeout of the acknowledgement. And then this PT0N0, it represents that acknowledgement timer timed out for the data sent with that semaphore variable. And if it is timeout, then again it has to retry. So again, this transition will fire TS0K. It will send a packet with the same sequence number, which has been for which I have not received any acknowledgement. And this will fire only when the value of K will be less than N, because I have to try only couple of times, that is N. Okay, so and then if the data packet has been sent, which is represented by TS0S, then it will send the acknowledgement, and which is represented by TCOM1, that represents the data unit, sends the pack acknowledgement to the embedded unit with sequence number 0. So it has sent the acknowledgement, and P in the PSW0 where there was a token, it was waiting for the acknowledgement. So definitely this wait will be over, so the token will be pulled out from this PSW0 and from the PR1R, which was representing that acknowledgement number with that particular sequence number has been received, and then the successful transition will fire, that is TS0 acknowledged success, ACK-SUC. So it represents that acknowledgement with sequence number 0 is received and the data send is completed successfully. And again, the token will be deposited in PDSR and PSRDY. But before that, I want to touch upon one more point, that when after a couple of trials, again it is failing and the acknowledgement has not been received, then the transition will fire is TS0 ACK USUC, which represent that the process of the data send is terminated without success of N trials. And this transition is fired when K is greater than is equal to N, because up to N it will keep on retrying. And when this situation arises, then I'll have to report that data send is unsuccessful by putting a token in a place PDSASU. And one interesting point is that and the successful is representing by PSUC, data send successful, is reported to operator. And one important or interesting point is that in this figure, the left half image is the mirror image of the right half. And why? Because I have considered the two embedded units for improved reliability, so that if one embedded unit fails, the other embedded unit can take over. Similarly, if one I have taken the two display unit also and two communication modules also. And so, and I am sending the alternate package from the alternate embedded units. And this also provides the online testability feature. Now let us try to let me explain what is online testability feature. Suppose you are having two generators, and the light is, and you are working very sensitive on a very sensitive and crucial task where you have to have light on all the time. And suppose suddenly the light has gone and the generator has started automatically and you started working on it. Now suppose at one time you say when the light was not there and the generator is on demand and it also did not come up, then what you will do, you have to take the help of the second generator. Now suppose in that case, suppose the second generator is not working when it was on demand, then what will happen? You will be stuck, and hence you can do either two things. Either you have to do the periodic maintenance of the second generator, which is on a standby and not in a continuous running mode, while first generator is in continuous running mode. So so here it is online testability or is already there, or either but there is a one lacuna. If you will go for the periodic maintenance, for example, at the interval of 1 month, and suppose after maintenance and after 15 days it stops working, but again you will come to know after next period during the next periodic maintenance, which is scheduled after 15 days, further after 15 days, and suppose after failing it after 2 days, your first generator fails and you are in the demand of the second generator, then you will come to know it is also not working and you will have to compromise with your crucial task. And hence it is always better, like if some part in a day you can perform from the first generator, some part you can perform from the second generator, so that all the time you can ensure like both the generators are healthy. And this is what this is known as online testability feature, and which is basically taken into this in our case. And now here the model parameter. Next, after construction of the PatriNet, we have to assign the model parameters, where the use of the machine learning and the artificial intelligence comes in, where you have to make the statistical model and you have to assign the delay parameter of each and every transition, which can be derived from the similar kind of projects. And you might have a lot of similar kind of projects, similar kind of systems in which you have a lot of data, and that data is basically you are doing the clustering of that data by feature extraction using the MATLAB coding, and then you may apply the Bayesian estimate to compute the most accurate data, and these data you can feed into the transition. So there are a lot of tools on which you can create a PatriNet model, for example, the TimeNet, Battery, CTN. So here the TimeNet tool has been used, where you can embed all this transition delay, and you can run this tool to obtain the throughput of each of the transitions. Throughput means number of transitions per unit time. So it is a firing rate, and these are the throughput that we get, right? And now the next is you have to construct the reachability graph, and in the reachability graph you have to, as I said, you have to identify all the possible states and the token distribution of among the places represent the state of the system. So for example, if you see in this figure, the token was only in the two places, that is PDSR dy and PDSR. So if this is the initial marking or initial state, you can see the places are in the two places. The tokens are only in the two places and rest all are zeros. Similarly, when the tokens are in these two places, this transition will fire and the token will be deposited. One token will be here and one token will be here, because the weight of the output arc are 1. So you can see here the next state will be from here. The token has been deposited, the token has been removed, so it will become 0, and here it has been deposited, and here it has been deposited, and rest of all are zeros. And in this way we can keep on deducing all the states, and these states are tangible because you have assigned some delay on the transition. If those are having the zero delay, it will be the immediate transitions of vanishing marking. But these are the tangible markers. And just for the sake of the convenience, I have just mapped all these transition firing rates by lambda, mapped in for all these firing rates to lambda 1, lambda 2 up to lambda 12. And now we have to construct the reachability graph, and this is the reachability graph that we have constructed, that we have already seen, and it can be equivalently transformed into the Markov chain, because as I said, each of the markings are nothing but it's the state. So this is the state, and all the lambdas are representing the firing rate of that particular transition. So this is a Markov chain creation. And now we have to create a generator matrix. So definitely you can write in the MATLAB. You can create the, and how we can create the generator matrix. Just go back. Okay, just let me first explain here only. So if you see, like you have to write all the states, which is from M0 to M9 in the rows and the columns. And if you go back into the Markov chain from the M0, it is transiting to M1 with a lambda 1 transition rate. So the self transition will be minus lambda 1. So M0 to M1 will be lambda 1, and all are zeros because it is not transiting, and the self transition will be minus lambda 1. And that can also be seen with the help of, that equation. Let me go back to the same slide where I was discussing this equation. Just a moment. This is what this equation is. So you can derive all the diagonal elements from this equation. Coming back to the same slide. Yeah, so now you can see from M1, it is transiting to M4 with lambda 11 and to M2 with lambda 3 transition rate. So from M1, it is transiting to lambda 2 and lambda 4 by lambda 3 and lambda 11. So the diagonal elements can be calculated by minus summation of all. And in this way, we can derive the generator matrix. And now you have to compute the transition probability. The transition probability from one state to another state can be solved with the help of very simple logic. So if you want to calculate the transition probability from state I to J, you have to normalize the transition rate. So it will be equal to transition rate from I to J, and you have to normalize it. For the normalization, you have to divide by sum of all the transition rates from that particular I to rest of the states. And if I is equal to J, all the values will be 0. And this is the way like you can compute a transition probability matrix. So you can write the program in the MATLAB and you can solve it. And now you have to use those two equations where I was discussing the stationary distributions, which are the important equations, these two equations. So one was M0 plus M1 plus up to all the, so all the sum of all the states will be equal to 1. And the second equation is nothing but it is written here. So this is the final states, and which is going to remain with the previous states in the case of a stationary distribution, and you have to multiply it by the transition probability matrix that you have already solved with this, and then you can solve, and after solving you can come to know the state probabilities of a system in every and all the states. And if you so these are the probabilities of probability of the system being in M0 state, M1 state, M2 state, and so on till M9. And now, if you go back, if you see like M3 and M8, these are the failed state, because here there is the acknowledgement of the uh, packet is not successful. So either you can do one thing, because the behavioral states are many and the failure states are only M3 and M8. You can sum up M3 and M8 probabilities and you can subtract it by 1. That will give you the quantification of the reliability. And that is what, like here, I have done. So I have just added the state probabilities of M3 and M8 and I have subtracted it by 1. And it will give you the reliability of the entire communication module. So this is all what like I wanted to share, and we have seen how we can compute the reliability of the particular system using the mathematical modeling, and how we can make the use of the artificial intelligence, and we can make the use of the machine learning, we can make the use of the MATLAB, and we can make the use of the mathematical equations. So, and we have seen it taking a case study where I was interested in calculating the reliability of the communication module. Definitely, if your system is very large, you can break it down into the various components with respect to the essentiality and non-essentiality, or with respect to the criticality of the functions, and probably the functions which are more critical in nature, you can go for such kind of analysis, as failure of those functions may lead to the very severe consequences. So in case of any questions, I'll be happy to answer.